running.
Okay, so I want to demo. Make sure you get that mostly on there, right? So I'm just running a test now with the draining tank. It's the HVT setup, which I'll describe a little bit. And we're running in draining tank, and if you can see right now, what I'm doing is we have an exit jet of water, and I'm just collecting it in a bucket so I don't make a flood in the lab. But what's happening is, if we look at what's happening in the tank, we have about a 3-inch inner diameter tube that's full of water, and it's draining through a series of pipes and coming out an exit nozzle. And so we're using this to demonstrate a lot of fundamental thermo and fluid mechanic principles. And if what we're with the monitoring the depth versus height, we're doing a direct measurement of the height versus time, and we'll be able to do some data analysis, use mass conservation principle to find out what that exit velocity is. And then, of course, we can apply energy equation and come up with a theoretical prediction and compare it to it. And if we look, so what we have here is the flow right now in this position is coming through this 2 elbows and then out to the exit with a small exit nozzle, and get a height reading. And there's a lot of plumbing fixtures, so we can run this in different orientations, and there's a couple of manometers that are set up in this device so that we can get we can run it in different modes. And now we'll just let it play out and finish this test. So what we're going to do with this video is we're going to take it into Tracker and use that as a way to just measure that draining height versus time and do whatever analysis that we need to do on it. And then a team of undergraduate students is going to be doing this. You'll see this video, the test itself takes just a couple of minutes, and so I bring in teams of 3 or 4 students at a time, and they run through and they collect a raw set of data. And then we have several different nozzle configurations with different exit diameters, and some of them have tapered inlets and some of them are sharp inlets, so we see some subtle differences in the behavior depending on the precise design of the nozzles. And then we can compile all that info, and a class of 30 undergraduate engineering students get this kind of hands-on feel. So it fits really well in either a fluid mechanics course or a thermo course, and even a design course, because one of the things that I want to do is, instead of just having the exit jet come out and collect it in a bucket, actually show on the film, right? So the jet is much weaker now. Before it was shooting out, so now the depth is higher. So get back on the data. So, like, for example, a good senior design project would be to build a Pelton wheel to try to convert some of that exit jet energy, kinetic energy, into try to reclaim it in some way. Have it raise a weight, for example, have it drive an electric generator and see how much energy it can report. So you can see as it gets closer and closer to the end, it gets slower and slower, which is kind of intuitive, but we actually now have a measurement of what that is. And it's basically so what we'll do is just take a quick shot of the exit jet now. So now it's just coming near the end. Go back to the tip here. Try to make that perpendicular as much as possible. Yeah. So Eamon and I, my cameraman, have been doing this, but with a much larger exit jet, and the whole event takes like a few seconds in those cases. But with these small exit nozzles is what we want to really focus on in class. And now it's just dripping at the end, and it's pretty much done. So I think we could call that a wrap.